Now we're going to talk about the second kind of improper integrals of type 2. And remember, these are integrals where the interval is not infinite, but where the function has a discontinuity. Something goes wrong with the function, either at a or b, the endpoints of integration, or someplace in between. Usually the discontinuity will be an infinite discontinuity, so there will be a vertical asymptote, is the kind of thing we will deal with. If the discontinuity happens at b, which is the upper end of the interval that we're integrating over, the upper limit of integration, then what we do to integrate from a to b is, well, just go almost to b, right? You go from a up to some t, and then let that t get closer and closer and closer to b from the left. So the picture looks like this. We have this function, and it maybe goes up to infinity at x equals b. And instead of getting all that area, so that all that area is what we want, instead of integrating from a to b, we just integrate from a up to almost b, so some t, and then let that t value move to the right and approach b. So the limit as t approaches b from the left of the integral from a to t. On the other hand, if the discontinuity is at a, the left-hand end of the interval, this integral is defined to be the similar sort of thing, the limit not from a to b, but from just past a to b, t to b, and then we let t approach a, this time from the right, because it'll be sort of scooting in from the right. So here the discontinuity is at a over on the left of the interval, and we want all that area, and we just take a t value just slightly to the right of a, and then let it approach a from the right. Well, what if the discontinuity is in the middle at some point c in between a and b? All we have to do is we take the integral from a to b and we divide it up. First go from a to c, and then from c to b. We can do this anywhere, but we have to do it if c is a discontinuity. And once you do this, the interval from a to c is that first kind at the top of the slide, the kind of integral where the top bound has a discontinuity, because remember c is the problem. So that's a limit of an integral from a to t as t approaches c from the left. And this other one, we have to use the second rule, the one where the lower limit of integration is the discontinuity. So it's the integral from t to b as t approaches c from the right. So each of those is a limit. And the picture looks like this. I've got a, b, and then somewhere in between them is c. And c is the location where weird stuff happens with my function, maybe a vertical asymptote, like so. And so what we're doing is we're taking the area from a to c plus the area from c to b. And each one of those, remember, we have to do in this limit way because they're improper integrals. So we add up the two. Both of those improper integrals from a to c and from c to b must converge in order for the entire integral from a to b to converge. Otherwise, the integral diverges. So just like with the other kind of improper integrals, these can either converge if the limit exists and equals a number, or they diverge if the limit doesn't exist or equals infinity or negative infinity. So we'll do a quick example. Let's try to find the integral from -1 to 8 of the function 1 over the cube root of x. Notice that this function has a discontinuity at x equals 0. When you try to plug in x equals 0, you get 1 over 0, and that's a problem. The graph of the function looks like this. So at x equals 0, we've got an infinite discontinuity, a vertical asymptote. From the right, the function goes up. From the left, the function goes down. And what we're looking for is that net area in green. Remember, that's the area above the x-axis minus the area below the x-axis between x equals 1 and x equals 8. So since there is a discontinuity at 0, we have to split up the integral as the sum of these two. First, -1 to 0, and then 0 to 8. You split it at the discontinuity. So this is the kind where the discontinuity is in between the two endpoints. Okay, that first integral, from -1 up to the discontinuity, we write that as the integral from -1 to t, and then let t approach 0 from the left. The second integral from 0 to 8, we have to do the integral from t to 8 and let t approach 0 from the right. So if the discontinuity x equals 0 is at the top of your integral sign, t approaches it from the left. If the discontinuity x equals 0 is at the bottom of your integral sign, t approaches it from the right. Okay, these are easy integrals. To integrate x to the negative 1/3, you add 1 to negative 1/3 and you get 2/3. So it's 3/2 times x to the 2/3, and we'll plug in t and negative 1 and take the limit. And 3/2 x to the 2/3, plug in 8 and t and take the limit. So that first limit is 3/2 times the cube root of t squared, that's what t to the 3/2 is, minus the cube root of negative 1 squared, that's what negative 1 to the 2/3 is. And the second limit, likewise, is the limit of 3/2 times the cube root of 8 squared minus the cube root of t squared. Now, as t approaches 0, in this case it doesn't matter whether it's from the right or the left, because the cube root of 0 squared is 0. So both of those terms go to 0, which means all I've got left is the 3/2 times negative cube root of negative 1 squared and 3/2 times the cube root of 8 squared. So 3/2 times the negative cube root of negative 1 squared is 3/2 times the negative of 1. And 3/2 times the cube root of 8 squared is the cube root of 64, that's 4. So I have 3/2 times negative 1 plus 3/2 times 4, that's 11/2. Since I got a number, the integral we started with converges and it equals that number, 11/2, or 5.5. And I think that's all. Let's see. Yep. Alright, so now we know how to do improper integrals of type 1 and of type 2. We'll have lots of chance to practice in class, and I will see you there.